Time I see fragile inside of a box, I can't help but think of the Christmas Story. Look, Dad, it says fragile on the side. It must be from Friends. Oh. FedEx actually did their job and packaged this one right. Okay. Okay. This is the third Tokyo high power I looked at this week. The other two are awaiting parts at this time. And I have the feeling I have the same thing going on here. So this gentleman sent out, it says fragile. Okay. This gentleman here called me because he's got, this is a Tokyo high power 1.5 kW. We talked on the phone pretty extensively for a long time about this. Hey, thanks. You sent me the power cord. Right on, man. Okay. Sent me the manual, which is a good thing. It's the big boy. It's the big boy. Anywho. Back on topic. I'm sorry. He sent me this because every time he goes to put power to it, it pops the very specific Tokyo high power fuses. And he wants to know why. And I said, well, send it up here. Well, come on. Thank you, big girl. We'll figure it out. Okay. We got this. Okay, I got it. Okay. I'm getting old, man. Getting old weak. So this is the Tokyo high power 2.5K. So this is the legal limit with the LCD display. This is one I haven't looked at yet. I'm familiar with the little brother of this. The 2.5K FX. Okay, so we took the lid off. We did a very slight visual inspection. What I mean is we stood here with a flashlight, looked at everything and made sure nothing was too overly borked off. You know, like nothing's got major burn marks on it or scorch marks. These are straight from Tokyo high power, 16 amp, 250 volt. The 1R, 1KA, AC, DC, 250 volt slow blow Tokyo high power fuses. The customer states, this is what the customer states. Where's the note? Notes here underneath the box of fuses. Customer states, blows fuse when I take it out of standby to operate. I'm sure I had it keyed up with no antenna, wasn't paying attention, and the tuner was on the wrong antenna. There's no antenna where there wasn't, he had the tuner where there was no antenna attached. Okay. It might be the final section, but we're not going to jump to that conclusion right away. So what I have done is I took the final section out. So we very delicately disconnected all of these wires and set it aside. The final section operates on a 300 volt final. Okay, it's called an AR 1500. Amazing transistor. This is one of these transistors that you could literally take like 120 volts and bring it in off the wall and use a simple doubler circuit and get your 300 volts, and you wouldn't even need to have a transformer for it. It is a MOSFET. It's not an LD MOS. It is a MOSFET. Hold on, I got one over here someplace. Hold on. So this is what they look like. This is an AR 1505. It's the part that replaced the AR 1500. There's two of these. Yeah, it's got a ceramic substrate to the back of it, right? Interesting and different, right? I got one of these plus a whole pallet to go around it. It's roughly a 1500 to 2000 watt component, mono-banded. So then if we spread that out and do all the appropriate filtering, it's about a 1000 watt device to make it work on all bands. Well, they've got two in the final section in this amp. Now it is and there's a reason I've got it inside of an anti-static bag inside of an anti-static bag that sits over there way out of the way and no one ever gets to touch it. They're sensitive. They're delicate little gems. They're not like the ruggedized MOSFETs that we're used to dealing with today. That being said, this is a freaking Tokyo high power, okay? It's supposed to have every modern safety interlock circuit in the world, and we've devalued the component to half of its rated output value. You'd think it would hold up to one or two keys. You'd think. Now, weirder shit's happened, and I wasn't there when it all went down. I'm just coming in here after the fact. Well, I am looking at this from the let's plan for the worst and pray for the best scenario. I've already looked at a couple things on that pallet. We'll get to that in a minute. But what we've done by disconnecting the pallet is protect it. If I turn this on, and the reason I remove these incredibly rare fuses and set them aside is because I don't need to have, 32 amps worth of fusing. I really only need to have like one or two. We're not going to operate it. We're just going to simply turn on the device. So our interlock is in place. He said as soon as we take it out of standby and put it into operate, it would pop the fuse. I'm not getting even the operate indication. So let's flip around here to our fuses. And we are plugged in. Nothing is mechanically shorted that I can see. I put 5 amp fuses in here. That fuse looks okay. That fuse looks okay. Are we not getting good connection? Let's test our fuses. That fuse is good. That fuse is good. Now, according to the block diagram, main fuse, safety interlock, which is this switch here, 12 volt sub power supply, transformer, relay, AC power relay. So the whole theory is here that I should be able to turn this on, and if it blows the fuse, then we know it's in the power supply side of the section. If we turn it on and it doesn't pop the fuse, then we know it's the amplifier side of the power supply that's killing everything and blowing the protection fuses. But for right now, let's see if we can get it just to power up. Let me redact my previous statements. First off, you can't power this up without the amp board being attached. There's thermal interlocks that are present to help you protect yourself from the board being too hot. So if you fully disconnect the band board, I disconnect this board here. I don't want to be sticking my fingers near there. If we disconnect this board and then the board that's underneath it, and then we disconnect this probe here, there's two safety circuits that are attached to this amplification board, and they both have to do with heat. But we still have the primary voltage disconnected. Okay? So our initial test is going to stay true. Now, in the previous video segment I said that these were the replacement for the AR1505. They're not. That was a mistake on my part. The AR1500 is its own separate special little unicorn. It's a 125 volt period device. The 1505 is a 300 volt device. Big difference. Completely different animal. Roughly the same amount of power. 750 watts a piece average out of each one of these devices. So we'll be lucky if we see 16, maybe 18 before the protection circuit kicks in. But I digress. It says everything's okay, we're good to go. Now I have it short fused with like 5 amp fuses in the back. If we flip this to operate, because he says this thing will do turn on, but as soon as you hit that operate switch and it goes pow, well, then we know we got a problem in our voltage supply. So, because right now we have 115 volts, 113.4 volts, 113.5 volts coming out of the power supply, which we have directly probed, but we don't have it hooked up. Now, I'm going to put on the safety protection, which is earmuffs, aluminum foil on the crotch. Let's get some dishwasher gloves for our practical exam here. And let's flip that operate switch and see what happens. Contact. Straight into protect. But we're not blowing the fuses. We'll reset. Please wait. Confirm checking. Condition okay. Voltage. All right. Everything's open. We're in standby. Directly into protect. But the amp's not shutting down. I'm not sure. I had it keyed, no antenna, blah, 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 blah. Blows fuse when you take it out of standby to operate. Well, we're definitely not blowing the fuses. For sure. So, that means we have got a problem in our final section. Is it a bad unobtainium transistor? I don't know. We're going to figure it out together, though. Sure is pretty. Directly into protect. Fuse blown. Protect, fuse blown. All right. Operate. Condition okay. Stand by. Proto fuse blown. All right, let's dig in. Okay, so if we get in the manual, and it says right here in the book, PROT fuse blown. It's a not resettable thing, okay? check fan control unit, unit 10, and PA unit 13. So we come back here to, here's unit 10, which in turn drives 13, which drives a fan control unit. I'm like, there's got to be some other fuses, but I don't see it on the quick block diagram. So I thought, well, I'm going to lift this board up and see what's going on underneath here. This is the 12 volt supply. I'm going to take a look underneath this board, and I flip the board over, and I'm like, oh, look at that. Open fuse. Imagine that. There's a fuse holder here and a fuse holder here. Okay. So off of our 120 volt filter cap, we go to a solenoid. The solenoid in turn dumps out here, goes through both of these fuses. So it's telling me that one of these is most definitely popped, or there's a circuit on here that's popped. So we're going to go problem solve that here in a minute. 16 amp fuse. This one is good. This one is bad. Tricky little bugger. Well, that's a two-sided board. They can see that there's no voltage going to here, so it's throwing it in to protect. Okay. Well, we're going to put like a 5 amp fuse in its place. But see, there's nothing hooked to it right now. Nothing. This is our plug for our final section, the PA section right here. There's nothing attached to it, it's just hanging down here in free space. So there's 125 volts DC, so we want to kind of keep our dick beaters out of here. And I bet you if we probe here, set our voltmeter to here, we're not going to see anything until we flip this operate switch. So let's go ahead, we'll plug the unit back in. Powered up. We're going to let it go through its startup process. It says everything's happy. Now we're in operate. Look at that. Voltage off, voltage on. Okay. At least we know what department we need to go look in. Put this in operate. All the band selectors are working. We got to go into this very carefully. Carefully. Like I can't just, oh, it's working, let's slam this together. Oh, it'll be fixed. I want to check, I want to see what caused the fault. Because I have a fairly good feeling that if I plug in positive on that thing, it's going to launch that fuse again. And if I repeatedly keep subjecting the thing to a bad short, eventually it's going to cause other problems, which I'm not going to be able to get parts to fix. The AR 1200 or 1500 components still hard enough to get as it is. I mean, like straight up. So hopefully you don't have a blown FET, but it wouldn't surprise me. Okay, I can't find anything on the final board that's popped. Like the final MOSFET's not shorted. Gate collector to emitter, or gate to drain. Pardon me, gauge, sort, drain, none of them are shorted. Nothing's open, there's no protection circuits open on the board. I'm wondering if when he took the thing and it was not attached to an antenna in transmission mode, if the current draw got so high on the transistor that the fuse blew, but protected the transistor, because I'm just not seeing anything here in the final section that's open. Usually when, like my AR, like when I played with the 1505, when they go open, it's a shit's flying, smoke. Children in Africa are like, damn, what was that just blew up? I'm not seeing any of that. So I went ahead and I short fused this. Again, we're relying on the fuses to protect us. These are 5 amp fuses. There were 16 amps that were in there. Everything's hooked up short of the coax connectors at this point. I'm just kind of curious. Oh no, we got a short for sure. So that's the thing, it's already broken. So we know for sure we got a short over here. And the 5 amp fuse popped, just the way it was supposed to. And it's 100% downline and it's on the RF board. Okay. This is definitely a gate to drain problem, I think. Okay, I just want to show this to you real quick. Let's power this up. The only thing I did was I disconnected the amplifier board, replaced our popped 5 amp fuse, and I wanted to show you that none of the other circuitry in the amplifier was harmed, so we haven't done anything wrong. There's nothing here that we haven't caused any more damage than what's already been in the amp. So what's broken is still broken. We just now know which department to go look at. Let's get this unplugged. We know it's in this department here, because we watched the sparks all together on video here just a minute fly off together. So either the transistor is blown or something in the flybacks is let go, and it's letting, as soon as we apply the 118 volts to the final section, it's this side that's causing the problem. Freaking trippy, man. Pretty sure we got a blown FET. But now I'm going to pull the final section out of here. We're going to button all this back up because we don't need to mess with this, and I don't want to have the chance of any of this getting damaged, because pretty sure I got to go on a hunting mission now to see if I can find these parts that are in here. But let's get this out and let's figure it out specifically what problem, what, where, physically, who, with how many jelly beans. So let's get this out and I'll put all this together. We'll be right back. Okay, I'm going to stand here and talk just for a minute. So I went back and reviewed the video, and I could see the spark that flew right out of here. Let me show you what we found. It's going to come across way better in pictures than it is going to be with me zooming the camera around a bunch. So about now, we should be coming in onto the kind of close-up photo. Here, let me help you see it even better. All right, back over to us here. I just ordered 2 brand new AR 1500s from, pardon me, ARF. So in the gun world, my brain says AR, and it's got to be bad. It's got to be a break. It can't be ARF. I just ordered 2 ARF 1500s from Mauser. After shipping an overnight delivery to guarantee that they'll make it here by Tuesday, was a little bit of money. This is a $700 fix. Now, I'm not going to tear this all the way down. There's no point in taking this RF deck all the way apart, or the PA here all the way completely apart, until I have the transistor in hand. But what I am a little bit kind of curious about is if we have a drain issue going on, Man, that attenuator is something fierce. Backed up with another huge attenuator. This is our whole input circuit. So, yeah. It's got an attenuator on the bottom here. And that big white brick there, that's an attenuator as well. My biggest fear is that the gate and the drain are shorted in this one part, and that it's shorting against the gate voltage circuitry. And has that whacked anything else upline in the chain? Now normally, what I would do, or anybody else that I know that's in this business, what we would do is for each one of the gains, or the gates, we put like a little 1.2 ohm, like maybe less than a watt resistor in line. And that would usually fly open when we have a hard short like that. But as you guys can clearly see in those pictures, and maybe I get close enough for you guys to see it. That is straight effed off. So, and I was with the customer on the phone. I said, you know, if it was up to me, I wouldn't trust, you know, I'd pull these transistors out. I'd do both of them. Just saying. And he was with me. He's like, nope, we're gonna do one. We better do two of them. I said, all right. So I'm gonna fold this up. I'm gonna put this in plastic. I'm gonna set this aside. I'm gonna put this back in its original container for a hot minute, and we're gonna come back to this. So the next time you see this out on the bench, through the magic of television and electronic digital editing, it'll be 4 or 5 days from now. Okay, so as far as you guys know, it's been like 2 seconds. To me, it's been over a week waiting for parts to show, which we've got. All right, here. I almost opened a bag. Started to, and I thought, no, they're going to want to see that on camera, so I stopped. But today, my only mission is to get in here and take this apart, and then I got to test a bunch of stuff. So I took about 100 pictures of this thing, and the only thing I've done now is I peeled back the power wires. This is the thermal temp cutout. That's what this goes to. I'm assuming this is our bias, our gate voltage. I've got to take this whole mess off the top of the transistors, and I got to do it one layer at a time. And I'm not too sure how I'm going to do that. So I'm going to freeform this and just keep going. I'm going to start working on it. I'm going to call this 1, 2, 3, and 4. So I'll mark them. I'll come in here and hit them with a Sharpie. 1, 2, 3, and 4. That's all got to come out. All of this has got to come apart. Now down in here, they've got labeled 4.36, 4.37. I'm assuming that's our gate voltage. We're going to find that out here in a few minutes. But this whole board, the flyback circuit, this is our input tune, all this stuff, this whole section's got to come out. These disc capacitors have got to come out. And then there's a shield that's underneath this piece of aluminum that's got to come off. You can see it here. So I will be back as soon as I get this layer of the cake taken apart. Input tuner board, flyback and combiner circuit, our pass-through circuit here, and now we're down to here. This is a little bit of a trip to get this all pulled apart, but next thing is we got to pull these shields off. And remember that these transistors are held down by the pressure from these plates and aluminum sinks. So I'm just going to go through here and I'm going to peel up each corner one at a time. We're going to take the shield off, then I got to get out the hot iron, and I got to lift up each leg one at a time, and hopefully we can get this to come out of here. This is a special high temp solder, so I'm having to add Kester to it, dilute it, and then I'm going to have to wick it. So it's going to take a little bit of time, but I'll be back. What I wanted to show you was, here's our burn mark, our arc over. And you can see where the arc path came right out of the transistor this direction. So I can't wait to get this up and see what kind of damage we've got to the actual device. And then we're going to actually pull the device apart so we can see on the inside of it. Let me just say, kudos to the Tokyo high power engineers. Brilliant. And once I say this, it's going to become very, very obvious to everybody else involved. It took me a couple minutes to figure this out. So I had the board all bolted down, and I go to start removing the shield. Well, I was able to get that leg up fairly easy, and that leg up fairly easy. I went around to unsolder this one, and it would not come. And I'm going, man, I got a 100-watt welder on that thing. That should just fly right out of there. Just this little piece of tin. Well, I struggled, and this one came up. And I'm like, man, I hate having to leave the iron on there that long. And so then this one came around, and it would not come. I'm like, what the hell? I'm down in there with the solder, you know. I am not going to mess the traces up on this. I'm going to do this right. I'm not in any kind of hurry, right? So I ended up having to get out the 150-watt iron, and finally was able to soak enough heat to the joint quick enough to get the shield to come off. But then immediately the solder joint went, it went back solid. And I went, what the hell? And then I started thinking about the last Tokyo high power that I did. And I thought, man, I wonder if they've got underneath this tab, this tab, this tab, and this tab, a bunch of vias that are copper filled, and they're going directly to the heatsink. So when I go and I get out my FLIR and I measure the heatsink temperature, and the heatsink is scalding hot. I'm like, God, it's brilliant. To keep the transistor from overheating, or the tabs from overheating for any reason whatsoever, they put vias for the ground side of things. So it takes the heat and soaks it right from the via right down to the heatsink, out of the circuit. Oh, man, okay. I just know that every single thing that I unhook or have to hook back up, I'm opening myself up for another possible solder joint issue, another broken wire, a bad pin, something. So I'm trying to take this down as minimally as possible. That, and some of this stuff is just straight up epoxy down. Like, this is a filter, believe it or not. Oh, and I misidentified this earlier. I said that this is a combiner. It is not. This is their pass-through flyback circuit. It's really cool. This wire goes to ground, but then it hops out over here for the drain side of this. This side goes to ground, and it hops out and it comes to the drain side over here. Well, it's completely decoupled. There's no physical connection. It's brilliant. This is... That's neat. I cannot wait to try this in something else. This is a neat piece of technology here. For another, it's a whole nother YouTube video why that makes it so cool. I want to Google what this part is. I know what it is on the schematic. I just want to see what the value is. So I went ahead and I undid everything and I popped the board up, and guess what? I was able to get everything to come off like lickety split. So this is our good AR1200 transistor. Now that I'm a little bit wiser, smarter, older, and wiser, just like the rest of you now, spent an hour and a half, almost 2 hours getting that one out. I bet you I get this one out in 2 minutes. So I can't wait to see what's fried from this. I cannot wait. So by picking the board up and setting it on the cardboard, I'm no longer fighting a heat sink, but these are all the solder pads I was talking about. Now the reason I got to go back and inspect all of these is I've got to prop this up, and now I got to come back and I got to solder wick all of this, because this has all got to sit smooth. Like I've had flow through now, like on that one pin and here as well, where a little bit of solder is wicked down through the vias, and it'll keep the board from not sitting flush on the copper. So I got to do a little bit of cleanup work here, but I got both the parts out. So let me do the delicate cleanup work on this, and now we're going to go test the AR 1500s. Okay, so board is all set up for reassembly. I got it bolted back down again. And no, your eyes aren't deceiving you. They have elevated copper pads for this to land on. Now I cleaned it first with 91% rubbing alcohol and then with another stuff called choline, which is a high temp, very low conductivity. It's got a very high dielectric to it, cleaning compound solution. So that's all prepped up. This is all the solder wick I had to use to get the components up off the board. And with a mixture of hot air and right size soldering irons, we're able to get the transistors up. This is the one that had the problem, so let's test it. That's the beauty of this Atlas, is you can check anything. Even ceramic coated MOSFETs, ceramic foot anyhow, which I can attest to conducts heat very well. It burnt my fingies. Blue, green, leads shorted. We knew that going in. Okay, so we know within a shadow of a doubt that this part is junk. Now let's go take a look at its partner in crime. So gate, source, and then these four outer tabs are drains. So pardon me, gate, source, drain. So gate, source, drain. Outer four, source. Let's put it through our little test procedure and let's see what we get. Ooh. Green and blue leads shorted. And that's something. Didn't see that coming. Shorted, shorted, and short. So both of these FETs are popped. All right. Huh. Only stands to reason. Okay, well, I want to pop the top off, which there's a seam that goes right across through here, and through here. And these legs are about the thickness as tinfoil, so we gotta be really, really careful we don't snap the legs off. But since these are both borked off, it doesn't really hurt anything. All right, let me get set up for that. All right, let's see if we heat this up. Boy, we're just failing all kinds of ways here. Come here. Oh, this is not going to end well. Oh, well, it didn't take much motivation. Lid just came right off. Oh yeah, that part's fried. Fried. Look at that. That's cool. Well, now we know what the inside of an AR-1200 looks like. Yes, sir. Whoa, worse than the other one. Wow. I mean, that came apart with some serious anger and frustration at the world, didn't it? Wow. Grab a photo of that. Let's get in here with the camera. Wow. Okay, well, those two parts are definitely fried. Son of a gun. Son of a gun. All right, let's go test some other parts and then we'll get ready to put this thing back together. Okay. Attention. Electrostatic sensitive device. Yep. That is the way parts should show up. Nice package. Tab length is significantly different, but the footprint is the same size. So, okay. Looks like we're cutting it. Yay. Oh, it's only gold, Luke. Only gold. No problems. Just so we know, we bought this from Mauser. Okay? Do not buy these kind of parts off of eBay. No legitimate parts dealer is going to sell you a part off of eBay. I mean, Henry Radio for elements and slugs and a couple other small things, but no legit transistor dealer sells through eBay. Especially from China. Do not trust anything that you buy from China through eBay. It is fake ass fake. So These legit were over $400 a piece, shipped directly from Mauser. It's like, got a friend of mine that's got that other high power I'm working on right now. N-channel MOSFET. 3.665 is the gate. I want to write that down. 3.665. Anyhow, I call him up and I said to him, hey man, here's the story. I said, the legit parts dealers have got those at like nearly $400 a piece. And he goes, clears his throat, goes over to the computer, and I hear him typing. He goes, well, I just found a set on eBay for $189. I said, okay, well, 3.665. I said, you do that. We're going to make that the right one. I said, do you want to trust that? I said, dude, that's a fake. And then I went and I looked up the same listing. And it's fake as frig. I mean, it was in those shitty plastic bags that scream at you, I'm from China, don't buy me. .665. Okay. I've only got one shot of this to get this right. I don't have another RF board that I can pull apart and test. So I'm going to have to get out my current probe, and a lot of work to get this to turn on properly. But have faith, we're going to do it. So let me throw some thermal goobly-goob on this, and let's get these transistors down and soldered in place. I want to concentrate on that, so just, I'll be back. I mean, that is a lot of stuff around those transistors. And that's a lot of work. Especially like soldering the transistor down. I kind of tacked it in, and I had to pull the whole board up, solder the transistor the rest of the way, and then set the whole thing back down again. Only to have to promptly lift the whole board back up again to put the shields on. But it's all back in one piece. And this was a nightmare for me. Because it is a Series 1 FET, it is incredibly susceptible to a lot of different things. So, yeah, static and heat and all kinds of stuff. But needless to say, it's all back in one piece. So let's go ahead, let's get the amp out and let's put it back in there. So here we are the next day. This thing has occupied a lot of my time because I do not want to mess this up. Normally I go into a lot of these projects and I'm just like, you know what? If it's a little off, it's okay, I can adjust to it. But this is one of these deals because the finals are so stinking expensive. It's $700, $800 worth of finals in the end of this amp. I am not risking nothing. I mean, I'm like triple, quadruple checking everything as I put this back together. I'm checking every resistor, every capacitor, every diode, everything. Making sure everything's laid perfect. I mean, solder's perfect on this thing. I redid some joints like 3 times until I was like, they're perfect. The big thing that's had me kind of hesitant is the gate voltage, because when I probed that yesterday, it was 3.665 and 3.665 per unit. I'm like, I don't know, man, that seems a little high to me. So then I look down here and they were kind enough to put it on here. It tells me a couple different things. This is a delicate part, because it's a delicate part attached to an incredibly expensive thing. And what I mean, they were kind enough to put it on here. The date, the year, what adjustment A09 was adjusted to 4.36 volts. And adjustment A11 was adjusted to 3.37 volts. And that's factory certified. So that gives me hope. Well, we don't have the 120 volts hooked up, but everything else is in. We have it short fused at 5 amp, even though that's not going to come into play right now because we don't have this hooked up. But I think I'm ready to fire it down and put it through its motions and test our gate voltages and make sure that we're within spec. And if we're within spec, then we'll go ahead and we'll hook up the 125 volts, cross our fingers, put the aluminum foil cup on our balls and see what happens. Okay, I think I'm set. Double, triple checked everything. With this being disconnected, the FET should be relatively safe. So, contact. Condition is okay. We're going to put it into operate. This is 19 degrees Celsius. That means all of our temp, and I'm reading this here. Means my temp probe's hooked up properly. Now the way that we have this hooked up now is directly to the gate on the opposite side of the capacitors. That's our voltage that's present. We're going into transmit mode. Okay. So now, the camera's in the way where I need to be. No, I'm not digging this. Hold on. Okay, so let's switch sides of the circuit. And the way our gate works is it comes off this bottom board, and then it runs up these two wire leads that go off each side. So we're going to probe the right-hand side, the one that had the catastrophic failure. And we're seeing 0.1726 of a volt. And then we're going to go and we'll probe down here. I don't want to stick my hand anywhere in there and call me chicken. Over here we're seeing 2.913 or 2.915, 2.920 and fluctuating. Which is what I was afraid of. Go ahead and shut this down. I gotta pull the band board off, and we've got to go figure out what's going on with the bias circuit down here on the board, because we're not getting any gate voltage to control the part. So if I put 125 volts on this, it would not control the component correctly. So let's continue on. Okay, so this is a little bit of a blessing. We're going to let this go through its startup process. Put that into operate. Now we've disconnected the leads. These are the leads that carry the gate voltage up to the devices. The green one, black wire goes up this side, and the purple and black wire goes up that side. So let's go ahead, we'll reach in here, we'll probe. We'll put it into operate. 4.62. Where before we couldn't even get a quarter of a volt. And we'll probe here. 3.53. Come back off the key again. So what that's telling us is that the bias board is working and it is applying the appropriate amount of voltage. It's just something up chain has shorted and it's pulling whatever the bias board's putting out, it's pulling it to ground. So there, now all the high voltages bled off. Did 125 volts. Make you tingle and do a happy dance voltage. This circuit here. So The gate voltage comes out of the control board, runs up through these two leads, and as we can clearly see, the black wire ties to ground, and then this green wire here ties to an insulated pad which goes to this resistor, which then goes to the gate, and then this blue tantalum capacitor here, I'm assuming, is open. So when the transistors decided to fart out their guts, the resistor did its job and acted as a shock absorber between the gate control board and the transistor. And I bet you when we go to pull that tantalum and this tantalum on this other side, that we'll find that they're wide open and they're short in the ground. Let's go ahead and probe this. Dead short. Probe this. Hello? Not a short. This side's a hard short. So let's go ahead. I'm going to start taking this apart. We're going to double check that. And we're going to look at the other side as well and see where we've got ourselves getting pulled, all the current getting pulled to ground. So, I mean, it's pretty straightforward. This should not be going to ground. Yep. Okay. Let's check it out. So we got this all taken apart. Oh, for the love of Pete, Snickles, come on. Nancy Pelosi's always getting in the way of anything. Okay, here we go. All right. That tantalum is open. Like, open. Open. Well, okay. So we know what we got to do here. Now, what's going on over here? Let's go look at the other side. Okay, this isn't surprising, but this is what we're dealing with. So we got two different problems here. Let's go ahead and let's clamp on this resistor here. We'll go ahead and we'll probe down in here. And it is showing that's 311 ohms. Now it gets even better. Let's switch sides. Let me clamp on over here. This is why we were seeing different results per side. This one's showing us almost 30K. Here's the problem. I didn't bother to check these two. The two resistors I didn't bother to check are messed up. Let's look at the color band on this. Red, red, black. That's a 22 ohm 5 watt resistor. 22 ohms. Not 330 ohms and 22K. So, okay, I gotta hunt down a tantalum capacitor and I gotta come up with 20 ohms worth of resistance for a safety circuit. I think I can do that. Okay, so we replaced the tantalum and then we replaced the two resistors, or that resistor and that resistor, with two 5 watt 10 ohm resistors. And what's 2 ohms amongst friends? I can adjust for that with the trimmers. So this is coarse, and this is fine adjustment. This is fine adjustment for this output, which is this FET, and this is fine adjustment for this output, which is that FET over there. Okay. So let's do the world a favor and very gingerly take these apart. This thing's been apart so many times now, I'm starting to really... I don't like to take things apart more than maybe once, maybe twice, because then you end up starting chasing cold solder joints on plugs and all kinds of stuff, right? So let's go ahead, we'll probe this output, which is this adjustment for this MOSFET, the green and black. This is the one that was hard shorted. Okay? Kick the amp into operate. That's a little high. I can trim that down. That's not a big deal. Okay, 3 or 4.8. Let's go ahead and let's trim that down. .36 volts. That's what it wants. That's pretty close. So now we can go ahead and hook up our circuit, which is, remember, an inductor back in here on top of the MOSFET. We got an inductor which is 100 or 1,000 ohms, basically, worth of represented resistance that couples to ground. Then we have our our 20 volt or 25 volt tantalum capacitor at 3 UF, and then our 20 ohms worth of resistance go into the component. So here we'll see 3.92 now that we see that the load, the resistive load that's in the circuit. Reprobe. So we'll go over here and we'll probe at the top, the 10 ohm resistance. So we've got adjustable voltage. I can adjust to that, and we got to adjust to the part in operation. What we're trying to achieve is a stable environment. Now, let's go to this plug port, which is adjusted here with this trimmer, which is for this MOSFET on the left-hand side of the screen here. So probe in here. It's got 4.97 volts. I lift my foot off the pedal to go back to zero neutral, okay? We know this circuit's working right. This one on the right-hand side, it's working right. The one on the left, we still have a problem with, and I don't know where it lies yet. So I'll plug this in. We had 4.91 volts, right? Watch. Drops to 1.47. So something on this side of the circuit, and there's a capacitor that comes off this, the gate voltage, there's a capacitor. The capacitor could be open. There's a tantalum over here that also tested good, so I put it back in. I might need to pull that out and replace it. And as we know, this guy was at 22K. Well, we replaced it with a 210 ohmers, so we got ourselves a 20 ohms. It's close enough. 22, 20 is close enough. This represents too much current. If I was to take a current probe or put this in current mode through here and measure this, it would show that this entire circuit, which is about 1 amp, most of the current is getting used. There's something still shorted in that circuit. But this side, the one on the right-hand side, is testing great. So now if I choose to take the green and black wire and disconnect them and go and hook the purple black wire up into the same circuit for the green and black wire over here, which we know this circuit here is working right, so we'll hook back in over here. .91. It's a completely different result than what I just seen. It's not even 5 seconds ago. I just tested this off camera and it showed me a completely different result. Now, according to the schematic, here's VR3. This is our coarse voltage adjustment. That's here. And then we have our VR2, which is here, which adjusts this, and VR1, which is here, which adjusts this. So did I have the coarse the coarse voltage adjusted so low that the fine voltage could not be adjusted properly? It might have been a case. Let's flip this around. We're going to grab that here, and then we're going to take our probe, make our probe ground. So disregard the colors. This isn't going to be color specific here. Okay, so, okay. And now let's grab this other fluke. Let's slide you over. Make that probe common. Come around and we'll not electrocute ourselves on the 125 volts DC. Okay. And now, with our non-Michael J. Fox hands, okay. So this is coarse. This is fine, and this should be for the meter on the right only. Which will make it after that other 10 ohm resistor. Let's not guess, let's know. Okay. Let's flip-flop this back around. Make this common. Yep, that's hot. Return that to common. I'll probe here. 3.71, 3.61. Okay. And then we'll lift the whole circuit out. .95. So put us right at 4 volts to get this number. Put us right at 4 volts on the transistor in operation. So we're looking for 4.36. We'll go a little on the shallow side of 4.35. Then we'll put the whole circuit in line. .21. We'll probe here. 4.18, which will put us right at 4 volts on the transistor itself. Okay, well, it was me. Apparently I had the potentiometers adjusted inappropriately. So let's set up our other gate voltage and let's move on. So plug that. And this one it wants 4.37. Okay, let me get out the amp gauge. Okay, I think I'm ready. I'm going to go with a lower gate voltage, the one that's suggested by the transistor checker. So this represents this FET, that one represents that FET. And it wants to see, according to the transistor checker, it wanted to see 3.665 and 3.665 for the transistor to turn on. So we're at 3.68, 3.69, but then you've got to remember there's another 10 ohms of resistance that it's got to go through. So that'll put us right at the threshold for the transistor to turn on. And if I pull the leads out of line, or disconnect the bias leads on the board, it's at 4.35 volts on this one, and 4.357 volts on this one. 4.3, it's a tenth of a volt lower. So in circuit, everything, the way this is sitting, everything is perfect. I'm sorry, I don't want to run into this and like, oh, it's all going to work, slam together, pow, parts blow out of it. I do not want to be burdened with this thing coming apart. So we're walking into this slowly. I'll let our high voltage bleed off. Okay, there's 19 volts DC there. So these are short fused at 5 amps apiece, these two glass fuses. Okay. Now here's the part that scares the shit out of me, is when I flip this operate switch, which will engage that contactor and will bring the 125 113 whatever volts online to make this transistor work. So let's do it. I didn't blow the fuses. Step on the pedal for zero signal. Okay. Waiting for the FLIR to boot. Waiting for the FLIR to boot. Okay, FLIR is booted. Nothing's getting hot, nothing's running away. Let's put it all back together and let's see if it makes power. Kind of wandering around in the dark when it comes to this transistor. I have a lot of experience with the 300 volt part and its characteristics. I don't have so much experience with 125. I have a lot of experience with the 65 and the 50 volt components, right? That experience, you learn a lot of different things, like where the sweet butter zone is for the gate voltage and how far you can really push it and how far you can't. There's a lot of surface mount technology that I don't have replacement parts for on here that I would just love to change, but let's just say I'm kind of feeling like I'm down here in the dark a little bit, but it's okay. So we're going to put about 2 watts in it. We're going to go to 80 meters. And it's either going to make power or it's going to immediately blow up. And it made power. Hallelujah. I pulled the short fuses out of it and I replaced it with the 16 amp fuses. Speaking of which, I want to watch my current draw. Because anything more than 16 amps and sayonara finals. I know that to be a fact, Jack. So let's see here. Shoot, this just ain't working out too well here. Okay. So, putting a water so or so into it, and it's pulling an amp on that side. So let's turn the power up. Watts in is making 100 watts out. 1, 2, 1, 2. There's 200 plus watts. I wish I could run this and have it laid splayed open. Okay, let's go to sideband on 80. SSB. Hello, 1, 2. That is not going to be an accurate form of measurement. We're going to look over here on the 1000-watt element over here. Hello, 1, 2. Hello, 1, 2. Just shy, about 18 watts input. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Hello, 1, 2, 1, 2, 1, 2. 500 watts with 20 watts of input. Okay. Let's go ahead and we'll bring the power up a little bit now. Hello. About 25 watts worth of power. Hello, 1, 2. There's 800. I'll bring this on up a little bit more. Hello, 1, 2. Hello, 1, 2. There's about 50 watts worth of input power. Hello, 1, 2, 1, 2, 1, 2. Hello, 1, 2, 1, 2, 1, 2, 1, 2. And the meter down here in the front is an average. It's working. All right. Okay. I don't want to get too carried away, because the way this amp is designed to operate... Oh, I didn't get an amp reading. Hold on. Got to get an amp reading here. Hello, 1, 2, 1, 2. 5 amps. Okay. Beauty. Beauty. The way this amp is designed to operate is that air gets pulled through the heatsink and then exhausted out the amp. Nothing in here is getting cooled the way it should with the case being open. I'll put the case on it and let's give it a whirl. Okay, so we're going to start out on 160. And we're going to go to autofocus so it actually can do its job. I apologize everybody for my sloppiness in camera work in the last couple sequences and events here. This amp has made me very, very nervous, and I'm incredibly grateful to see this thing running. I said not a lot of experience, now I got it. It's like the first time you touch a boobie, you know. And I don't want to be the thing that's like pantyhose. You know what they say about pantyhose? Yeah. I don't want to be like pantyhose, the thing that destroyed finger blasting from like the 1950s forward to today. Just saying. So, anywho, I'm gonna put about 50 watts into it on 160. There we are. Okay. Hello. 900, 950 with 50 watts in. I am not in the mood of trying to push this to its maximum watts. Just not. Let's go to 80. Hello, 1, 2. Once again, 50 watts in on 80. Amplifiers on 80. Radios on 80. Just kind of interested to see how this is going to work all the way across the bend. First time I've ever gotten to play with one of these, but I've gotten to play with all its little brothers. So, hello, 1, 2. Hello, easily a kilowatt with 50 watts going in. Let's go on up here to 7 megahertz. Sideband, once again. Okay, hello, 1, 2. Same amount of drive, 50 watts. Hello, 1, 2, 1, 2. Hello, 1, 2, 1, 2. Look at cleannesses on the spectrum. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Ah, it's a beautiful thing. Let's go up here. Hello, 1, 2, 1, 2, 1, 2. This swear is 0. Not 1, 0 input. Hello, 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 hello. 1 2 1 2. Okay. Hello, 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 hello. All right. Hello, 1 2. Hello, 1 2 1 2 1 2 1 2 1 2 1 2. Hello, 1 2 1 2 1 2. Hello, 1 2 1 2 1 2. The reason I'm doing this is to help myself build confidence in this amp. Because the longer I can sit here and talk on it, it's only picked up 9 degrees Celsius since we started. The longer I can sit here and talk on it, the more confident I am in what we got going on here. I guess would be the best way to put it. Hello, 1 2, same amount of drive. Let me show you the front of this thing operating here. Back this out just a little bit. Hello, 1 2. Hello, 1 2 1 2. Hello, 1 2 1 2. So the old burr meter is pretty accurate with the meter on the front. It's showing that we're doing about around 500 watts. Meter on the front. Short of half kW. So spot on the money. Do 18 megahertz first. Hello, 1 2 1 2 1 2. I'm gonna get me one of these one day. It's kind of cool, just twist a knob and away you go. But I like tubes. I like tubes. Hello, look at that go. Look at that go. Hello, hello. Hello, 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 hello. Back down here. Hello, 1 2, hello. Hello, 1 2, hello. Back over here to the spectrum. Hello, 1 2 1 2. Back up here to the red radio. Hello, 1 2 1 2 1 2. So I can give this back to the customer and be like, no, I'm 1000% sure that it is working on all bands over a kilowatt plus. What did you do to it? Not that he's gonna, because this guy is really chill. All right. There's meters. There we go. Hello, 1 2. 24 megahertz now. Hello, 1 2. Hello, 1 2 1 2 1 2. Step on the pedal. Hello, 1 2 1 2 1 2 1 2. See a little bit of dirt over here. Hello, 1 2 1 2 1 2. It's so far down from the principal, we don't care. Don't care. Hello, 1 2 1 2 1 2 1 2 1 2. I don't know if this is modified or not. We're going to find out. Hello, 1 2. Oh yeah. Hello, 1 2 1 2 1 2 1 2 1 2. This is its lowest output band of them all, the 28 megahertz band. Check this out. Hello, 1 2. Hello, 1 2 1 2 1 2. Okay. So to my CB friends that are watching and listening, because I got friends on both sides of the street, and I don't discriminate, as you guys all know. Do not buy the $4,000 amplifier to run on 11 meters. You will be very disappointed. The ham guy is going to love the shit out of it. So, it has been a long time since I had to spend so much time thinking about something, or even was a little bit nervous on camera. This thing gets an award for both of those things. Sorry, it's just an awful lot of money involved. Awful lot of money involved. I just got from the vinyl printer a bunch of new stickers. Let's see, are you going to come off of there, or are you going to be a little pain in the ass? Gentlemen, if you've enjoyed my little show and you guys enjoy what I do here, please come over and help us out on Patreon. Link's down here in the bottom right hand side of the corner. You could have had access to every single thing I'm working on, usually on a daily basis. I try to do a post at least once a day. This is what I'm working on. These are the problems I'm having. This is what I'm doing this afternoon, this evening. Every single question that gets sent to me gets answered. Take a minute, come help us out on Patreon, help this channel survive and become better and stronger. I got it set so it's $1. And if you want to donate a little bit more, I'll take that too. Make sure to come put your call sign and handle in the list, in the group. That way I can add you to the thank you list at the end of the video. Well, gentlemen, I'm going to call this a win. A hardcore win. And it was a lot of fun to get to work on this. All I had to do was replace these parts. Now, if you remember correctly, back at the very beginning of the video, I said that usually that there's a fairly low watt, in this case it happened to be 2 high watts, resistors of fairly low resistance value that act as glitches or fuses, in the best way to put it, to protect the bias or the gate voltage. Here we are. The use of the tantalum capacitor is brilliant, in my opinion. Absolutely brilliant. It makes sense. You put a 25 volt tantalum capacitor in that circuit, it's going to add just a little bit of capacitance to the circuit, but as soon as the voltage crests over, let's say 25 volts, pow, the capacitor is going to pop open, and it's going to pull everything to ground, and it's going to protect everything up the chain. Brilliant. Absolutely brilliant. This circuit has got me freaking thinking about some stuff. It really does. The one that's in this amp uses 10 ohm resistors, 4 10 ohm resistors. So a total value of 2.5 ohms. And the ground leg of each one of these, because these cross, okay, so this would go to this input, that one goes to that input or output lead, and then this here goes to a capacitor on ground, and this one goes to capacitor on ground. Sorry, this one goes to capacitor on ground for decoupling. This is neat. I cannot wait to try that and a couple other things, but gentlemen, the Tokyo High Power HL 2.5K FX. Restored back to its total glory and running like a Swiss watch. You make me nervous, you expensive box. Gentlemen, big thanks to Excess Power, Signalant, MechMan, Coaxial Dynamics, Bird. Of course, a big thanks to all of you guys. For those of you that stuck it through to the end, I'm proud of you, and I say thank you, and we're on to the next one. Whew. God, I'm glad to be done with this. I'll see you. Click, click.